So welcome back to this seminar regarding Bayesian statistics and cognitive modeling. So we've spent nearly quite a few weeks, more than half of the entire semester discussing the Bayesian statistics, and we have discussed some examples of the coin flipping and the globe tossing, and those are the applications to use the Markov chain Monte Carlo MCMC to perform model estimation or parameter estimation. It's always that we will begin with a research question, and for example, how much water is covering the entire Earth. So that is the research question, and we gather data. So we throw the globe up into the air, and then we catch it, and then to see if that is water or land. Those are the data. We gather the data. And then we use Bayes rule, right? We use the Bayes rule to model the process. And before that, we also need to come up with a data story. So how might the data arise? So for example, if we are in the globe tossing example, there is the underlying proportion of water covering the land, and this is unknown. And we come up with a linking function that is a model, D model, the likelihood function. In that particular case, that is a binomial model. So if you follow me, and then in that case, we use the binomial likelihood function. We can construct a model. So what is the known part, the water observation out of 9 times of entire experiment. The unknown is the parameter, the entire proportion of water covering the Earth. And then the model is the likelihood of binomial function. And given that, we could estimate the posterior parameter given the data. So that's the posterior. And also today, let's just switch gear, because we are doing this course not really for a generic statistics purpose. We are also talking about cognitive modeling. So from today, and we will be talking about this topic. And before that, what is basically cognitive modeling, right? So, and first of all, I would like to convince you or to encourage you to think about this fashion, that the idea of cognitive modeling or computational modeling is never new. So maybe you might just wonder that, well, it's aesthetic psychology, or maybe it's something a little bit similar, but in this area, linguistics, sociology, I never really learned so much about statistics or programming. So whenever I heard the term computational modeling, it just maybe seems too new, and at least sounds a little bit scary. I never understand the math, right? You might have this kind of concern, but computational modeling, the idea is never new, because it has been around for more than quite a few hundred years ago. Because when we were studying in high school, I guess, and we learned this, not maybe the exact math, but we learned this as a fact that those physicists, like a few hundred years ago, they were trying to understand how the planets are traveling around the sun. Maybe this is not correct from today's perspective, but back then people were trying to propose two quantifications regarding how the planet is traveling around the sun. So one can be like a circular, just a circle, and the other one can be this elliptical orbit. So it's kind of not a perfect circle, a little bit narrow and on the one end, and a little bit wider on the other end. So those are what are they? They are trajectories. They are how the planet is. They are the approximated trajectory of how the planets are traveling around the sun. And they are models, right? They are models, because you can write down the equation of a circle. You can write down the equation of this orbit. You can also, the elliptical orbits, you can also do that. If they are the mathematical quantification, then what are they? They are mathematical models. They are computational models. So it's never new. It's been around for a few hundred years old. It was trying to explain physical phenomenon or physical processes. And when it comes to mental process, then it becomes cognitive modeling, which is only terminology, because whatever you try to explain, they're just models, right? The model doesn't know what it is trying to explain, because the model can't really tell what is physical, what is mental or cognitive. It is really in the mind of the researcher. We are trying to understand the process, and we build models, not the model build itself or themselves. So in terms of cognitive modeling, it's basically the mathematical quantification of how the mind or how the brain works. This is like broader in description, but how does that actually work? Still abstract, but maybe a little bit more in detail. So we do experiment, right? We have a research question, for example, how do people memorize words, and how do people make decisions under uncertainty, and how do people navigate themselves in the physical space. Those are behavior that we can be interested in, and those are indeed interesting questions. So how do we study this kind of question? We ask participants to come into the lab, and we show them some experimental program, and we ask them to do the experiments. So this is the participant, and this is the computer, and we gather data, right? We gather data, we gather either button press, the data, we either gather that kind of data, or maybe some eye tracking data, EEG recording and MRI recording, MEG recording, whatever, you name it. We could gather different kinds of data, behavioral data, neuron data, those are the data. But you would imagine how or where does the data come from? The data doesn't come from the hand. It comes from the hand by the physical contact, but the data actually comes from the brain, right? Because the brain is doing something, and then the brain is trying to trigger the muscle movement, and then there's the button press. Rather than the finger is moving something, the finger doesn't think, the brain thinks. So what we do is like we use those behavior data and also the neuron data to try to understand what might be going on when the participant is doing this kind of task, for example, a learning task, a memory task. And we use this information to back infer what might be going on. So in this case, you can ignore here the equation, but what we can imagine is here the text. So if we know how the brain works, we could be able to predict the data, right? To predict how they behave, but we don't know that. What we know is we know the data, and we try to inverse engineering to try to understand how the brain works. So what is this, like posterior, right? So this is how can we understand. So look at here, the posterior, the format as a posterior. So this is kind of also a natural way to use the Bayes equation or Bayesian inference to analyze our data in behavioral science, psychology, or cognitive science, cognitive neuroscience. But anyway, this is also not so intuitive, because you have to consider many things to do the model inversion, and you still don't know what might be going on in the brain. So what can be done a little bit differently is like we could try to propose some models. So the model is approximation of how the brain works. So basically you can ask a model to do the same task as if this is the brain. And you could also ask the model to simulate choices or some other behavioral data or neuron data. And then let's say we propose or to construct a model, and we say, well, as if the model is doing the task. You could imagine this is just artificial intelligence, because this is artificial, but it is intelligent. It can do experiments, right? And the model can also make some button press, for example, and to choose A versus B, or maybe to memorize 10 words out of 12 words. And there are sometimes also the forgetting part. This is some just artificial intelligence. You can think about that way. And we propose a model, or we propose artificial intelligence. We ask the model to also predict choices, to generate choices. And what we can do then is to compare here, if the data generated from the AI or from the model could match the data from the real people, from the real participants. we do just compare if they match each other. If here we ask the model to make behavior, to generate behavior, then we can compare the resembling between the human behavior and the model behavior. And if we are trying to ask the model to generate some neuron data, then we could also compare if the real fMRI data time series also matches more or less. Well, let me say the other way around. If the data, neuron data generated from the model also matches the data from the real participants. So if this is a match, we could imagine that if you learn or hear or read from the news a lot, you would see the term a lot, like human-like behavior. So the AI is able to generate human-like behavior. So the behavior is like as if it is human, right? If then those match, we would imagine that in a certain, in a specific or certain circumstances, this model or this AI is a good approximation to how the brain works. So the idea, to put the long story short, is like if the prediction from the model could match the behavior of the real person, we could say this model is a good approximation to the brain. Okay, and you might be quite suspicious regarding this. You could imagine that, well, I could always generate or to construct a better model that beats the current one. So if you read the news also, there's the Google DeepMind, they always do some fancy stuff regarding artificial intelligence. If you also read the news from yesterday or maybe 2 days ago, they come up with a super interesting, there's a video, you can watch it later. Maybe I can try to find the link. They created a new AI. They created a football game, two versus two. Like usually a football game is 11 versus 11. This is too complicated, right? And then they started with 2 versus 2. So they had 2 teams, one blue team, one red team. So they are basically trying to do what real football players are doing. So there's one ball, and then they try to compete and then to win the control of the ball. And they also try to score it within to put the ball into the net, right? Into the back of the net. And there are many things to consider. So one is there's also the physical contact. So if the defender is if the defender is close to the range of yourself, then your ball control might be a little bit altered, because you have to first use your muscles against your opponents, and at the same time you also have to control the ball, and maybe against him the opponent is challenging, then maybe you also have to decide to pass the ball to your teammates. So those are interesting considerations. Try to mimic what might be going on in real football games. And if you watch the video, one thing when I watched it yesterday, I had 2 thoughts. One is that looks pretty real, pretty authentic, and this is one thought. The other one is there are some strangeness, because real players, real humans, they don't play football in this particular way. So you will notice both of these kind of like tastes or flavors. So then you could imagine that they maybe could be able to improve their model in the future, right? So here's the same. If your model is generating some data, if that matches, that good, but there is not a perfect match. It's always not possible to have a perfect match. So there will be some degrees of freedom you have to tolerate to allow for some randomness, because the model, because the behavior from human, usually you could imagine that consists of 2 parts. So one is the signal that you're interested in, and then there's also the noise, because some participants, their behavior is a little bit, from time to time, their behavior can be a little bit noisy or maybe a little bit randomness. And this doesn't have to be entered into the model, right? Because your model the main goal of your model is to explain the signal. You don't need to explain the noise, because that's not really part of the deal. So not part of the experimental design. But anyway, so what I'm trying to say is you could construct an infinite number of models. You can always have better ones, And you could always say that the current one is not good. You can have a even improved version in the future. So then there's this kind of saying, if you the quote, if you read like computational work from different places, and this is quite often quoted, is like essentially all the models are wrong, but some of them are helpful. So you never know if your model is correct or wrong, but those are helpful approximations, like to generate maybe human-like behavior. So maybe we could rephrase that a little bit to say, well, essentially all the models are imperfect because there is always the room for improvement, but some of them are helpful. So helpful for what? Helpful for, in our case, helpful for us to understand how people maybe make decisions, how people maybe learn stuff, how maybe people memorize words, how maybe people, I don't know, do stuff, cognitive things. There's a comment in the chat. So couldn't it be that observations and simulations, wait, there's another one. Let me get to the first. Couldn't it be that the observations and simulations from the model match perfectly, but the underlying cognitive process is completely different? Yes, it's possible. Yes, yes. So if like, yeah, as you said, yes, yeah. So even though the behavior is the same, but can be that people generate, or like the real human, the behavior that arise, this such pattern of behavior arose for different reasons other than the one that is proposed by the model, even though seemingly they look the same, but the cause can be different. Yes, it's possible. Yeah. So that's why understanding or studying cognition is not easy. It's freaking hard, honestly. So if more than one model works well enough, would the scientific community then also consider theoretical overlap to agree on which model to prefer, overlap with actual existing behavioral theory? I mean, so it's like most of the time, I would imagine, where does the model come from? So you would ask this question in the first place. So the model, they would actually come from some theory, right? So if there is existing theory, and then the existing theory is trying to explain some behavior, in earlier ages, maybe that theory is kind of verbal or descriptive, and is not so quantitative and cannot be quantified as the modern standard. So what can be done is there's the theory, so that's very good as a starting point already, and then you could construct your model based on the theory. And a even nicer scenario, maybe not for explaining the behavior, the nicer scenario for like doing a research project is like there's a alternative or competing theory. They are both trying to explain some kind of behavior, but maybe both of them are verbal or descriptive. What you can do, well, construct mathematical models derived from either of them, and then what you can do, you can just do model fitting, right? You could use MCMC, for example, that we will be talking. Well, we talked already. So to do model fitting, and then you can compare which model is the winning one, which model is not winning, and then the underlying theory that is backing up that winning model is perhaps more favored in this case. Or maybe I'm answering your question in a different direction. I'm not sure. Does that make sense?
Yes, thank you.
Okay, cool, thank you. Well, maybe there's another scenario, like maybe you could also able to construct a model that isn't having some theoretical background. Maybe it has, but not directly from the existing theory, because the new model would argue that all the existing theories are wrong or are imperfect. Then some researcher, they would propose a new model and then try to outperform all the others. But then the new model, it will also have some theory, right? So maybe they say, well, this theory is wrong, that theory is wrong, there's a theory that is also wrong. So then they propose not only the models, they will never start from the model, they will start from a theory. So then first they propose a new theory, and then deriving from that theory, they have a model, and then they can do the following step: model comparison, model fitting, model comparison, and then so on and so forth to get out the quantification, the results, the data, and then the results. Good. Other questions? I would imagine this kind of discussion here is rather theoretical or maybe sometimes philosophical, and it's always good to think about them. Great. So then we were talking about here, right? So all the models are kind of imperfect, but some of them are helpful. And so let's just talk about one of the quite helpful ones in the entire cognitive modeling. So cognitive modeling is a big field. And if you are indeed interested in cognitive modeling, there are multiple fields nowadays that you can look into. So first of all, like traditionally, not so traditional, but with a longer history, is the field called mathematical psychology. So mathematical psychology is not the psychology to study how people learn math. It is not the same. And if, let's say, there are researchers who are trying to understand the mathematical academic performance at school, so how students, how well they study, how well they learn math, or maybe if you heard something called I think it's called snack effect. So the ordering thing. I'm not sure if I described it correctly, but anyway, regarding how people read or sense numbers, and to compare if a cloud of dots is having more dots than another cloud of dots. There's something like that. Those are the psychologists to study math. And this is not the same as mathematical psychology. So mathematical psychology is basically to use math to understand psychology, to basically cognitive modeling, right? So if you look or read articles or papers in the journal called Mathematical Psychology, there's indeed a journal called Mathematical Psychology. Most of the time you see people propose models to understand behavior, or maybe they propose a new analytical perspective to analyze the same theory from quite a few years ago. And this is the field one, mathematical psychology. And field number two is perhaps with a little bit neuroscientific flavor or neuroscientific perspective, that is called computational neuroscience or computational cognitive neuroscience. So computational neuroscience, the field per se, is a little bit different than what you would imagine. It's like mostly I would imagine that computational neuroscience or maybe not up to, so maybe more than 70% researchers, they're animal researchers. They don't really study humans. So they study the animals, and they study, or maybe even the more lower level, like synapse and neuron specs and recordings like that. So those are the majority of the computational neuroscience. And then there's the remaining 30%, or maybe even less, or maybe a lot less, I'm not sure. Those are the human researchers. And they try to use cognitive models together with neuroscientific approach like fMRI, or maybe intracranial recording, EEG, and also you name it, to combine these kind of tools to understand human behavior. And a few years ago, maybe 3 years ago, those people, human researchers, they would try to kind of distinguish themselves a little bit from the animal or researchers, not to set the boundary, just to make it more explicit that they are human researchers. So then there's a new kind of term called cognitive computational neuroscience, or maybe the other way around, computational cognitive neuroscience, doesn't matter, same thing. So basically, they are human researchers, human neuroscientists who use one, computational models, and two, neuroscientific approaches to study human behavior, human cognition, and human learning, human decision making, human memory, human stuff. Yeah, those are the kind of new field. And then there's also a conference because of this movement, the CCN, Cognitive Computational Neuroscience. There's also a conference called CCN, and it now has the third edition already. The fourth one was planned last year, but because COVID didn't happen, it didn't take place. This year, perhaps it will take place, but most likely online. It will be the fourth one. If you are really interested, I encourage you to take a look. And maybe also to register if that is free to attend. All right, human neuroscientists, cognitive computational neuroscience. And if you go to that kind of conference, you will maybe hear this term very often. So that is called reinforcement learning. And if you go to a CCN conference, I would imagine that kind of 40% people will focus a little bit more on the reinforcement learning. So reinforcement learning, what is that? So let's talk about this. And why we are talking about this is because it is, as I said, like all the models maybe are imperfect, but some of them are helpful. So reinforcement learning is one of the most helpful and impactful models in the field, in the CCN field. So reinforcement learning, maybe you also heard about that, maybe not. Where does that come from? So there are two kind of historical roots related to reinforcement learning. So one is from Pavlovian conditioning, so animal behavior, right? From 70s or like earlier. These are like psychological roots. And the other one is a little bit different. That's from engineering. It's from optimal control. And maybe if you have colleagues or friends who is working in the field of engineering, so one of the biggest challenge is perhaps to design machines that will behave precisely, right? So if you are like, let's say, designing or in the manufacturer setting, you want to just maybe design a cell phone, the iPhone here, let's say, you always want to make sure that your more robot arm kind of thing, I don't know how the term, so you want to make sure everything's precise. Otherwise, when you are assembling your cell phone, it won't work, right? Maybe the one side is bigger than the other, 1 millimeter bigger, then they don't match. The phone won't work. So this is from the optimal control of perspective, and this is also related to reinforcement learning. This has its two roots, and then 20 plus years old ago, 24 now, 23 years old, there was the new book back then. It was pretty new, a book regarding the introduction of reinforcement learning. So it was written by two computer scientists. So the Richard Sutton and Andrew Battle, and they talked about mostly from like computer science perspective and the engineering perspective, slightly about the psychological roots that I mentioned, like Pavlovian conditioning, animal behavior. And then since like 1998, and a lot of researchers from psychology and cognitive neuroscience, they picked up this idea, and they were like, well, isn't this the same or similar relative to the animal behavior that Pavlov was working on quite a few years ago? And then they found that this is quite interesting. There is the relation. And then they also used the tool reinforcement learning to study behavior. So early 2000, you see that there's a kind of quite an increase regarding papers like in psychology and cognitive neuroscience they picked up the idea of reinforcement learning to study human learning, human behavior. In between 2000 and 2005, there's a kind of a huge increase in this kind of area. And then the two authors, they are quite informed regarding this development outside their field. So in the newer version, after 20 years, there's a huge development, right? After 20 years. And then they also dedicated, I think, 4 or 5, a few, I don't know, many chapters, multiple chapters, discussing how this can be related or how this can be applied in psychology and cognitive neuroscience. And because they noticed that development of reinforcement learning in the field of human neuroscience, and then they also included that in the newer, the second edition of the book. Good. So reinforcement learning and decision making is quite related, because if you are trying to, I will show you the example later. Because when you are seeing like stimulus, you try to make the connection between the stimulus and then the response. And then what is the response here? Response is decisions, right? People make decisions. So reinforcement learning and decision making, these two fields are in a way quite connected. So on top of the CCN conference that I just mentioned you a few seconds ago, there's then another conference or another community which is quite overlapping with the CCN community. This one is called RLDM, so reinforcement learning and decision making. Essentially, as you could imagine, there are two communities of people or researchers, one coming from the reinforcement learning perspective and the other one from the decision-making perspective. So decision-making perspective, basically neuroscientists, psychologists, cognitive scientists, a lot, regardless of human or animal. And then the reinforcement learning people, they are computer scientists mostly, and also a few like engineering perspective. The RLDM is not an annual conference, is a biannual conference. So every other year. It is also pretty new. I think the first edition, it was 2015, and then 17, 19, and this year maybe online. Okay, anyway. So remember the year of the first edition of the book, so 1998. So after 1998, you see here, you see the two colors. Those are on the x-axis, the year of publication, and then on the y-axis, those are the relative frequency. So how the number of publications, basically. So here in this purple color, those are paper regarding cognition and cognitive science. And then the other one is cognitive science together with computational modeling. So what you can see is that, yes, because there's a tradition to study cognitive science, or the paper, they are more than the paper who combine both cognitive and computational. This is relatively new. But if you try to, let's say, understand the rate, so the increase, how much increase that happens per year, you will see that the increase is a lot larger in the blue color, which combines both cognition and computation. And then if you look at here, maybe these are the annual growth. So the cognitive paper, they are like around 10%, and this one together with modeling, also cognitive, and the annual growth rate is quite high. It's like nearly 3 times as the rate of cognition per se. What is happening in the chat? Okay, thank you. Yeah, those are the links. Yeah, those are indeed the links. Thanks, Annika. Great. So a few more examples, and like 1 year ago, just 1 year ago, there were a few papers that were published in those kind of high profile journals, and this one was in Science, and this in Neuron, this in Nature Reviews Neuroscience, and then this one in Translational Psychiatry. it's nearly the same date, right? So it's March 30th. This is also March 17th. The same day is March 17th, and this is also March 1 week earlier, 12th. So why I was picking up this kind of 4 papers, it was because for one, this slides was created back then 1 year ago, and for two, those are recent papers, like relative to the point I was making the slides. I think when I was making the slide, these things were just maybe 2 weeks earlier. And another more important reason why I picked up those 4 papers is because, for one, those are important papers. They are great studies, and for two, 4 out of the 4 papers, and 3 of them, they focus on reinforcement learning models. So even though reinforcement learning model, I think it starts around early 2000s, there's increase, but still, in nowadays, like 2020, 2021, 2021, there are still a lot of different things and unknown stuff that we have to tackle, and we still have to do research on. And this is just basically to show the importance of the reinforcement learning model. And if you ask me which 3 out of the 4 are focused on the reinforcement learning model, it is this one, and then this one, and then this one. This is a review, but the theoretical background is also reinforcement learning. And this one is slightly something different. So if you heard about something called drift diffusion model or diffusion decision model to analyze reaction time, this used DDM, drift diffusion model, to analyze reaction time. All the others are reinforcement learning models. In fact, the DDM, the drift diffusion model, and the reinforcement learning model can be combined. So there's the newer developments to combine these 2, I would say, mainstreams of models. And the combination of the 2 is also a quite recent recent movements, I think, younger than 3-4 years. Anyway, so let's get back to the basics a little bit, rather than talking about the most recent ones, because understanding the basics is the foundation to understand the most recent findings, right? So we talked about, like, it is important, it is helpful, and it is useful, and a lot of the stuff are like grounded around this theory, reinforcement learning theory. But what does that mean? So how can we use that? So one of the kind of the most straightforward example in the textbook is to use something called a 2-armed bandit task. So those are just bandit machines or slot machines, like in the casino. So if you pull the lever, and then depends on the combination of the 3 icons, you will either get money or maybe nothing. So especially if the 3 icons are the same here, I don't know if that is maybe grape or cherry, whatever that is. If the 3 are the same, then you can gain some money, right? So the idea why there are 2 is because maybe one machine is more rewarding. So if you play with this machine, maybe you could be able to win some money more often. So maybe if you play 100 times, you could win money 80% of the time, but maybe small amounts. If you win 1 cent, something like that. And then the other one might be the other way around. So if you play 100 times, you don't win often. You win maybe 5 times, so 5%. Perhaps the money you win can be larger, maybe €1, €2, but it is very rare. Okay. But even though I'm not telling you that one is better, one is more rewarding, the other one is not so rewarding. I'm telling you, I told you. But in real-time, real-life scenario, you never know. And there are just 2 machines that look identical, and everything else they look identical. Just the underlying algorithm of the machine is programmed differently by maybe the boss, the owner of the casino. So one is better, one is worse. You don't know, right? And then what you can do, you have to play with it. you have to really pull the lever to observe what might happen, and then to think about, to update your knowledge, to update your belief regarding if this machine is worthwhile playing machine or not. And in this two-armed bandits example, those are two, it's kind of straightforward, because maybe you play this one, you play a few times, you win, that then you think, okay, maybe this is a good one, but maybe you also lose the opportunity to win more. So then you will also have to explore the option of the other one, right? If you always play this one, even though you win, you don't know what's happening for the other one. And then you might also want to switch to that other one. And then if you play, and most often, mostly you lose, then you could confirm your hypothesis that, okay, maybe this one is indeed a good one, then I will never play this one again, I will only play this one. And then some other scenario is, okay, this one you play, you win, and then you want to explore the other one, but then the other one will also say win. Well, then in this case, what do you do? So this is a kind of a tie, right? You have to play more, and then after maybe 50 times of play, you finally find out that, okay, maybe this guy is good and this one not so, and the initial sequence of consecutive win is only random, right? This is only random. Those are kind of the strategy that you can play. Well, those are the two machines that are in front of you, but in real scenario in the casino, it is never the case that there are two machines. There are maybe 10, 20, and then in those cases, it can be turned into a 10-armed bandit task or 20-armed bandit task. You can't play all of them. Well, you can if you have enough money, because you have to bind these tokens to just insert into that machine to play. Otherwise, it can't, right? So multi-armed bandit tasks are different and difficult. But for simplicity, let's just talk about two-armed bandit tasks. So those kind of example are indeed the quite common experimental paradigms used in the laboratory. So a task commonly used in the lab is just the one I told you. To repeat it twice between n options or two options in this case. You play and you see the feedback, and then maybe you play again, you see the feedback, and then maybe you want to switch to the other one, you see the feedback, and you play. And so you would like to, because why you are playing this, for one, you want to earn money, right? You want to gain some profits, even though you are doing this maybe for fun. You don't care if you lose or win, you are just only doing that for fun. But mostly, I guess, you want to earn something, you want to win something. So this behavior has to be achieved by learning the properties of the bandit machine. So you would like to learn the property of the bandit machine. So what are the properties that you can consider? So one is the probability. So how often, if you play the machine will return you the reward, the money. And the other one is perhaps the reward amount. So maybe this one gives you money often, but then it's 1 cent or 0.1 cents. It's quite tiny. The other one, maybe it doesn't give you money often, but whenever it gives you the reward, that's a large amount. Maybe it's €5, for example. That's quite a lot relative to 1 cent, right? That's a lot, 500 times. So but how would you learn these properties? You learn this from trial and error, because you don't know the underlying mechanism of the machine. You play, you observe, and then you make some mistakes, and then you play again, and you observe, and then you make some further mistakes. So those are the learning process through trial and error, right? Yes, and then lastly, there's a goal in mind to maximize the overall reward. What can be a different goal here is like, if this machine doesn't give you money, if the machine gives you electric shocks, so it gives you pain, right? It gives you shocks. So let's say, for example, there is a cable attached to the machine, and then the cable can be attached to your forearm. And then let's say if you see the 3 colors or 3 icons in a row, then you don't get money. Instead, you get a shock. So then do you still want to play with the machine with higher probability to give a shock? No, right? You might want to switch to the other because you want to avoid shocks. So the goal is different. One is to maximize the gain. The other one is to minimize the pain. So it depends on the goal of the behavior, and then you might behave differently. So here, because of the feature or property or like phenomenon regarding the goal is important. People term this behavior as goal-directed learning, because there's a goal. People would use the behavior to direct themselves to the goal. So goal-direct behavior. Great. Any questions? There's a chat. Yes, that is indeed. Yeah. The new study from our lab last year. Yep. Any questions up to here? All right. So I told you kind of the scenario, right? But then what can be the strategies? You choose and then you observe and then you learn. And this can just be your strategies. So before making the choice, before choosing which slot machine you want to play with, you first of all would like to relatively roughly predict which one is more likely to return you the reward. And this is called prediction, right? You predict the value of the slot machine. So maybe you think, well, this one looks, at the very beginning, even though they are identical, you would imagine that maybe the left one is better. This is your prediction. And then what you can do is, well, you choose like accordingly. So if you think the left one is better, the left one has higher or better value, then you just choose this one. You just choose to play this with this machine. And after playing, after you pull this lever, you will see the outcome, right? And then use the outcome, you could learn and to update your predictions. So if you play, if you think this is good, and then you decided to play this with this one, and then it turns out indeed that this one gives you more reward, then this will reinforce you to play with this machine one more time. So this is to update the value. So basically, if you win by playing, and then you would imagine the value of this machine is getting increased, okay? And then if you play, and then if you lose, then maybe you think, okay, this one isn't worth it. It isn't worth it. You do not want to play it. The value is decreased. So this kind of looping thing, you play, you observe, and you learn, you play, you observe, you learn. This is quite important for this understanding. So how is that relevant for us, or maybe for the reinforcement learning scenario? So if you remember the one I showed you on the kind of the cover slide, I showed this graph. Imagine that this is the slot machine, right? The environment. The slot machine can be the environment, and this is you, a participant, a person, and playing with the slot machine. So what you can do through the environment? What you can do to the environment is to play with the slot machines. Those are your actions. And then your action here, left versus right to the environment, will result in some outcomes. So the reward or not. The reward or not, those are from the perspective of yourself. Those are the observations. You play, you either win or maybe not win. So those are the observations. And then what you can do, you use this observation to, together with your goal, to update your understanding of the environment. The left slot machine, the right slot machine, which one is better? After the updating, then you make a new action. So you select one more time, left or right. So this is kind of the easier graphical illustration of reinforcement learning. And there's rather influential review paper from 2008, the one in the middle. So they were trying to, those are the earlier people, or the people in the rather earlier ages, like 12 and 14 years ago, 2008, not so early, but earlier. Those are the people in the earlier ages, and they tried to bring in the idea of reinforcement learning and computational modeling to try to understand behavior. So here, what they did, they were trying to decompose or tease apart the decision-making or learning process into multiple steps. And here, what we can imagine is starting from here. So if you are a participant or you are just a person standing in front of the casino and the slot machines, the first thing to do is to represent the scenario, to represent the environment, to represent the problem you are about to solve. So basically, you need to figure out what you're supposed to do, right? Why am I here? I want to play with the slot machine to earn money. I'm sitting in front of the computer to do the button press, also to win some money from the experiments. Or in the study that Roman shared, I'm sitting in front of the computer from our lab. I'm sitting in front of the computer to press the button to try to avoid shocks, to try to avoid pain. And also this action might apply not only to myself, but also to some others, like related to pro-social behavior and also empathy, right? Those are the behavior you have to figure out what you're supposed to do in a new environment. So some analogy, I guess you understand what I mean already, but some analogy, if you need it, is like you go you want to go to hike, you want to go to hiking, and you could just take a train and then you get off at some station. And then what you're supposed to do is to look around. There's a sign, right? There's the sign for the hiking trails. Most of the time is on the yellow background, and then the black letters to tell you the destination of some mountain peak, and also tells you the kilometer, and also tells you the estimated time that you will be able to reach the mountain peak, maybe let's say 5 hours. So, but before seeing that, after getting out of the train and then getting away from the train station, you're supposed to find the sign and then to follow the sign to go to start with your hike. So those are the same thing here. And after you have figured out what you're supposed to do in a new scenario, what you are doing next is to predict which option has better value. So in the slot machine example, there are 2 slot machines. After figuring out what you're supposed to do, you're supposed to win money by playing, and you would predict which one is more likely to return you money. In the beginning, maybe you don't know because they're identical, but through learning, you will gradually find out one is better and the other one is not so good. So those are the valuation, or maybe evaluation or prediction. You predict which is better. And prediction doesn't mean you actually choose it. And then the next step is to act or to behave or to decide accordingly. So if you say the left is better than the right, then you will just choose left because you think left is good. After the action here, you will be able to see the result because the action is from you to the environment, right? The action is from you to the environment, and then the environment will return you some outcome. So those are the outcome that comes from the environment. And what you can do with the observation, what you can do with the outcome here, what you can do with the outcome is like you could use the outcome and to update your prediction. So you basically learn from the outcome, right? You do something, and if the action resulted in good consequence, then you think the action is good. If your action resulted in bad action, then you do not want to repeat it. So this is kind of the simple idea to try to decompose decision making or learning into multiple phases. Those are like related. So this one is an easier or simpler, simplified version of the graphical illustration of reinforcement learning model. So if you read papers from DeepMind, for example, this can be quite complex, but the core, so this can be a larger one, but always in the center, in the middle, the core part of their model is nearly always the same. There is always kind of a person or a system, there's an environment. The action comes from the system or the agent or the person, and the action goes to the environment, and then the environment will generate some outcome based on the action. Those are the observations to the system, and then the system will perform further or future actions to the environment. Any questions here up to the point?
Are the internal and external states in the same theory as in Carl Friston's free energy principle? Like the internal states are the internal models and the external states is the environment, or is this something different?
This is slightly different. Yeah, this is slightly different. Yeah. So I think the one you are referring is like, I try to not make mistakes, but maybe I will make mistakes. So here you are interacting with the environment, and then what you would update is what you think about the environment, right? Then in your head, in your brain, you could imagine there is a model you constructed for the environment. And this one might not be the same as the real one, but through action and observation, this one will become better and better. In the end, it will be much more close to the real environment. So maybe, and then here you would imagine there's a distinction between the external environment and then the internal environment. Is that what you're talking about, more or less?
Yes, I think so.
Yeah.
Thank you.
So from Carl Friston, if you, I don't really understand him so much. I didn't even start to understand him, but I think this is a slightly different framework. Maybe the goal is to try to understand behavior. Yes, this is the same, but I think the framework is a little bit different. Yeah, you could imagine those are like free energy and predictive coding and active inference. Those are like usually the term in the other framework. Other questions? I think the connection can be like this. So either if we have an internal and external environment or state, we are basically trying to understand what is going on in the world, right? The reinforcement learning model basically quantifies how the external environment, I should write this, the external environment is used to update the internal environment. This is one way to update using the reinforcement learning algorithm, but maybe there are other ways to update it. So maybe from the environment, the observation, you don't really calculate the value. Maybe you calculate something else, and then regardless of what you calculate, it always tries to update the internal representation of the world, and then it generates new actions from the participants or human agents perspective. They are not necessarily competing theory. They can be combined and connected. All right, so usually in the experimental setup, we don't show people slot machines. We show people something simpler, not so simple. So for example, these abstract symbols, and this doesn't mean anything. They are just two symbols, one is blue, the other one is yellow. And those are the slot machines. And what people do here is we ask participants to make a decision, the same thing as what they want to choose, the left versus right, to play with the slot machine. So after the decision, they will be able to see the outcome or the consequence. In this case, the participants get a monetary reward, 20 cents. Because this is a repetitive game and people have to do it multiple times, so the next trial shows up, blue and yellow one more time. The participants has to make the decision again, so blue or yellow. So maybe in a simple scenario, because choosing blue resulted in a reward, so why not repeating the previously successful action, choosing blue again, right? And then perhaps this time the person wasn't lucky enough, and then this time there's the loss, or you can call that punishment. So this is the simple experiment, the two trials task, and you see this quite often in the experimental work, and also including the one from our lab, the one just in the link. It's kind of a similar task. We also use this abstract symbols to represent kind of the slot machines, and one is more aversive, the other one is less. So more aversive means more likely to get shocks, to get pain. So here we could also divide the two screens into two stages. Those there are only just two screens. We can name them. So one is the choice presentation. So what the participants are supposed to do. They are supposed to choose to make a decision, and then action. So which one they chose, and then outcome. What's a consequence are resulted from the action. And we could then, if we are running this kind of experiment, like let's say we ask 10 participants, they come into the lab and they make the decision, and they make decision 100 trials. They repeat the experiment 100 trials, each person. And you could imagine those are the data you will have at hand. So then you will have the raw data, right, from the participants. So think about that. Think about what can be your data. So in this kind of experiment, you basically ask participants to make a trials, and then they'll observe the outcome. What can be your data? You can just tell me, think about it, or maybe in the chat, you can tell me. If you are running the experiment, after you collected your data, you open up your text file or maybe your Excel sheet, what you are supposed to see. What are your data in this case? So any idea? Okay, so my idea here is in the chat, correct choices. This is already one step further. So how do you know this is correct? So binomial is not the data. It is, you're already talking about the model, I think. What is the raw data? So if one person has a text file, something dot raw data underscore sub1 dot txt, something like that. If you double click, what you are supposed to see? What do you think you will have? Yeah, so what the choices are and what the outcomes are. Yes, exactly. So those are the data, the raw data before analyzing it. So those are the data, choices and outcomes, right? Those are the stuff that we know. So we know the choice. left or right, blue or yellow, and then the outcome, the win or loss and the win or loss. And we want to code our data in numbers, and we could use, for example, 1 represents blue and 2 represents yellow. So 1, 2, 1, 2, left, right, blue, yellow. And here the outcome, we can use like 1 and -1 to represent the outcome. 1 means a win and -1 means a loss, okay? And the other one, like from Martina, so I think her answer, correct choice, is the second step. So what can we measure? So what can we measure? We can measure the correct choice. So how often the participants are choosing the more rewarding option, right? So if we know as experimenter that the blue one is better, the yellow one is worse, we could analyze out of the 100 trials, after excluding the missing trials, out of those valid actions, how often they choose the blue. So in this case, it means the accuracy, right? This is the accuracy. And then the very last one is like, what do we not know, but what we want to know? We want to know the motivation or the cognitive process, why they make this behavior. So after 100 trials, people, if the participants can figure out after repeatedly making the trials and observe the consequence, they will figure out what is better, what is worse, and then they make decisions accordingly. What is algorithm? Why they behave this way? So those are a cognitive model, right? So one way is here, because we are talking about reinforcement learning model, we will use reinforcement learning model to understand this behavior. And those are the things that we will be talking about in the next a few minutes to have an introduction. Well, here it just basically says to choose the better, the more rewarding option. Great. As I mentioned earlier, there are two routes in the reinforcement learning field. So one is the optimal control from the engineering perspective, and the other one is the Pavlovian conditioning from the psychological perspective or animal behavior perspective. So if you know kind of the words Pavlov says, he never claimed himself as a psychologist, not at all. But anyway, this is the psychological roots from animal behavior, from Pavlovian conditioning. So we are talking about this part. We're not talking about optimal control. So Pavlovian conditioning, and we know that quite a lot, I guess. So it is like, if you could, yeah, I think you know that. I don't have to explain. So you basically establish the connection between the stimuli and the consequence, right? So even though the bell afterwards is not followed by the meat, you will still see like the behavior from the dog, for example. So then this behavior is observation. You see the observation from the animal, and how can we understand it a little bit like quantitatively? So in the 1970s, psychologists, they are psychologists. They also claim themselves as psychologists. They classify themselves as psychologists. Rescorla and Wagner, so they come up with a learning rule to quantify this kind of condition. So then later we call them Rescorla-Wagner learning or Rescorla-Wagner value updates. So how does that work? So before I tell you the Rescorla-Wagner model, I will also have to tell you a little bit regarding the differentiations about models in cognitive modeling. So for one, we will build cognitive models. The cognitive model is the place to explain cognitive process, and then to explain how we think the brain is trying to calculate and then to trying to compute. Those are the cognitive process. The Rescorla-Wagner is one way of cognitive process, okay? And after we construct the cognitive process, we would also like to bridge, to connect the model, the cognitive process, propose the cognitive process in terms of mathematical functions or equations, we want to bridge them to the actual behavior. So those are the observational model. So those are the observational model. You want to connect the known and unknown, right? The idea that we talked about. So Rescorla-Wagner is one of the cognitive model, the cognitive process. So now we can talk about what it is. And I can now first show you here this idea in kind of our everyday language. And it says that the expectation on the next trial equals the expectation on the current trial. So basically there's an old one, there's a new one. This is the old one, this is the new one. So how the old one could become a new one. So this is update, right? So it is updated by a learning rate weighted prediction error. So here's a learning rate, something called the learning rate, doesn't matter, I will tell you later. There's a multiplication. The learning rate multiply something called a prediction error. So what is a prediction error? Prediction error here means the reward minus the current expectation. So basically prediction error means the error of prediction. So how close your prediction, your current prediction is relative to the reward. So if your prediction is close to the reward, then you don't have a prediction error because, or small prediction error because your prediction is already nearly the same as the reward. You have a small prediction error. But if your prediction is quite away from the reward, then you have a large prediction error. So your prediction is not good. It doesn't match the actual outcome. So what does that mean in terms of learning? So we can construct just two scenarios. There are only two scenarios. The reward prediction error can be 0 if your prediction is perfect, or positive if your prediction is smaller than the reward, or negative if your prediction is larger than the reward. Okay, still not so clear. What does that mean? So if you would predict that I will not get money, this is your prediction, but it turns that you get money. What is your prediction error? That's positive, right? Because what you actually get is money minus what you don't think you will get money is 0. Then you will have a positive prediction error. So basically, you get more than what you think. Conversely, what is a negative prediction error? That means, well, I predict I will get money, but then I didn't. Then your prediction is, your actual result is worse than your prediction. Okay, so just either of these two scenarios, the actual outcome is either better or worse than your prediction. So if your outcome is better than your prediction, then your prediction will be increased because you want to be closer to the actual outcome. And if your prediction, if your outcome is worse than your prediction, so then that means your prediction is too high. You want to adjust it. You want to decrease your prediction, also with the goal to be closer to the reward. Okay, does that make sense? Kind of? Maybe? I guess? Okay. And the idea is, what is the idea here? So the idea here is error-driven learning. So you make some mistakes, you will make mistakes. The actual outcome is either better or worse, right, than your prediction, and then you make mistakes. You use this difference, the mismatch between your expectation and the actual outcome. The difference, you will use the difference to update your learning, and this is called error-driven learning. And then more formally, and if you read papers, also you will be about to review. They will also write down some equations in this case, and the equation here in the blue frame is essentially the same as in this one, red orange-ish color. So, but here it's basically written in mathematical notion. This one V of t is trial, right? Expectation on the next trial equals expectation on the current trial, okay, current trial t minus 1, good, plus learning rates, okay, this is learning rates, multiply that with prediction error. Let's just call the prediction error PE, okay? And how is PE calculated? The prediction error is the difference between the reward, actual reward, minus the current expectation, okay? So that the math or like mathematical notion is maybe in the beginning is a little bit scary to look at, but if you understand the meaning, it doesn't really tell you too much fancy. It just tells it only tells you that the expectation on the next trial equals expectation on the current trial and plus the learning rate weighted prediction error. Prediction error means difference between the reward and the current expectation. It's just written in the mathematical way, which is simpler and clearer to look at. Because if I show you this, maybe you don't really know what's going on. But if you are getting more and more used to it, you will prefer this kind of notion more than the one below, because this is kind of verbal theory. Like you describe what might be going on. This is verbal theory. And after the theory is verbalized, you want to quantify it with more degrees of precision, right? You want to quantify that. And how do you quantify that? You have to use math, right? Otherwise, how can you do it? So then you use the mathematical notion to quantify your verbal theory to make it more quantifiable. Great. And this is the simple idea. So your prediction can either be better or worse than the reward, or maybe the other way around is your observation can either be better or worse than your expectation. And then you use the mismatch to update how you would evaluate the option, okay? The prediction error is now simple to understand. And there's one thing that we didn't even talk about, that is the interesting part, that is the learning rate. So what is the learning rate? Learning rate, you could imagine that in the first place, this is the amount of prediction error that is considered to update the value, okay? So let's say this is a new one, right? This is old one, the old value. So if the learning rate equals 0, then the old one and the new one will be the same. So there's no updates. Whatever you observe, because you have a learning rate of 0, nothing will be changed, okay? In this case, in the extreme case. But in some other, in the other extreme case is like, if the learning rate is 1, that means 100% of the reward prediction error will be entered into the value update. So you could imagine that the learning rate is the proportion of prediction error to be entered into the value update. 0 means 0% of prediction error will be used for the update. 1 means 100% of the prediction error will be used to update the value. Anything in between is like, if learning rate is 0.2, then that means 20% of the prediction error will be used for the value update. 0.8 likewise means 80% of the prediction error will be used to update the value. Okay, kind of a percentage of prediction error to be entered into the value update. So far, so good. It's quite straightforward, but the learning rate actually works a little bit trickier to make a comprehensive understanding. So let me show you what I mean. Oh, wait, there's a question, I think, in the chat. What word do you use to start with W? I never seem to be able to tell. W. Do I have a W here?
Yeah, can you understand me?
No, where do I have W? Hello?
It's warble or something, but I don't understand. What does that mean? Warble.
Ah, okay. Yeah. Verbal. Just
Oh,
words.
sorry.
Yeah.
Sorry.
No
Thank you.
worries. Where was I? Oh yeah. So learning rates is like a percentage of prediction error to be entered into the value updates. But the full picture is a little bit trickier. So let's try to understand that like step by step. So let me give you one example, because here they are just arbitrary and quite abstract, and you still don't know what is going on. So let me give you one example. Say at the very beginning, you assign value of the two options. So we say the value of blue option equals 0, and the value of the yellow option also equals 0. Because at the very beginning, they look the same to you. There are two slot machines in front of you. They look identical. They are identical. In all their regards, expect that their reward probability is different, but you don't know that. So at the very beginning, you would say, well, they don't mean anything to me. I assign value of 0 to both of them. Okay, good. And then let's say after choosing blue, you get money. You get money, dollar, euro, whatever. After choosing the blue, you get money. So then we can calculate. Let's say, suppose we have a learning rate of 0.9. Suppose the value of first trial is 0 because we assigned it, we defined the initial value to be 0. So then, first of all, we can calculate the reward prediction error. Reward prediction error is here. The difference between the actual reward and the predicted reward. So what is actual reward? Actual reward here is a €1 or 1.20 cents. We denote that as 1 or minus 1 for win and loss. Because we have a 1 here, because we have a win here, then we say, well, this is 1 for the reward error calculation. And the actual reward minus the prediction. What is the prediction? Well, prediction is 0, right? Because I said here at the beginning it's 0. So then our prediction error PE in this case simply means 1 minus 0, which is just 1, right? Just 1. And the prediction error is multiplied with the learning rate because we suppose that the learning rate is 0.9. Okay, this is the learning rate multiplied the prediction error. And then this is entered into the value updates. So the previous one, what is that? That is 0. Okay, so we plug in or to apply all of the numbers and then do the simple math and then arithmetics, you get 0.9. Okay, so what do we have? We choose blue, and blue resulted in a win. So the value of blue changed from 0 to 0.9. Okay. This is t equals 1 and then t equals 2. Okay. So this is how it works. This is how it works. And you could imagine that the first value updates, if you get a win, it's always equals to the learning rate. So if you have a 0.7 here, this number will be 0.7. If this number is 0.3, this number will be 0.3. Okay, you can see now how the value is calculated or updated. And then let's say if you choose blue, always choose blue, and most of the time you get a win, and sometimes you get a loss, and then you could calculate the trial by trial value. And then what you can get. So what you can get, you get a curve, right? So in the background, this is the actual outcome sequence. You get a win, win, win multiple times and get a loss. You get a few times more win and 1 time of loss, and win, win, and a loss, and so on and so forth. This is actual feedback. And the curve in purple is assigning or assuming the learning rate equals 0.9 and assuming that you always choose the blue option, and this is the value update. It goes very fast from 0 to 0.9 because of the calculation I showed you. And then if you do the reward update for the second time, the reward error is not so large because the second time the reward error is 1 minus 0.9, right? You have a small reaction, you have a small prediction error because your prediction is already 0.9. The max is 1, your prediction is already 0.9. So then you have a small prediction error. You are close to the truth, let's say. And because the reward prediction error is small, then the update is also small, proportional to that. And a few trials later, your prediction is already nearly perfect to the 1 part, which seems good because you are trying to get as fast as possible to the actual outcome. It is good for now, but we have to understand that the update goes symmetrically in terms of if you have a minus outcome. So if you lost, whatever you learned in the past, it will just decrease a lot because you have a fast learning rate here. You learn fast for reward, you also learn fast for the punishment. It's like you are sensitive to the reward. If you see a positive feedback, you're very sensitive. Okay, this is good. But as soon as you have a negative feedback, you will say, I have a negative feedback, then the value will be dropped, regardless of how many positive feedback you have in the past, something like that. So maybe you are okay here for a sensitivity for the reward, but this is maybe too much oversensitivity to the punishment because in the long run, the negativity, the losses, they happen only occasionally. You want to maybe strategically avoid it or ignore it because they are just maybe because of randomness, because of probability, they happen, but they don't happen often. You might want to ignore it. So here you might want to have a less sensitivity. You do not want to have an oversensitivity to the punishment. So let's try to plot a little bit more curves when the learning rate equals 0.9, 0.7, 0.5, 0.3. You could see that in particular the 0.3 version, even though the value update is like slower when learning reward, but it doesn't go so much negative when the punishment happens. So here it doesn't have a negative oversensitivity to negative punishment. And here when learning rate equals 0.7 and 0.9, they're basically in between of this curve. And then this curve, you will see how that changes. Good. Does that make sense for now? I think we need to stop for a bit. I will not continue here. I'll just give you one more example and then we can stop. So how can you relate this to maybe everyday life in terms of learning, right? Oversensitivity to positive reward, some sensitivity to negative consequence, something like that. So imagine that you're in a relationship and you have a partner, boyfriend, girlfriend, and husband and wife. So let's say you have quite a nice partner and he or she is always attentive, and whenever you send some message and your partner will always reply very fast in a short amount of time, let's say 10 minutes, and very positive and supportive, very good. And you're happy with that. And then maybe it's one day and you send something to your partner and your partner didn't reply. And maybe after 3 hours, still no reply. And what you might think, if you have a large learning rate, you would imagine that, well, okay, something is wrong. And did I do anything wrong? And what if I did some mistake? What if blah, 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 something happened? And this is kind of overreacting, right? You might not want to overreact to this kind of consequence because maybe on this day your partner is having a bad mood or for whatever reason, exam failed or job interview failed or some weather is not nice, no sun for different reasons, right? You do not really want to overreact to this kind of scenario. But if you do overreact, this can be kind of thought as a high learning rates, oversensitivity to negative feedback. And in another scenario is like your partner is still good, but maybe you do not pick it up, and the partner is always treating you or considering very, very considerate, but maybe you're a slow guy, you're kind of a little bit nerdy, so didn't pay too much attention to this emotional stuff. And after maybe 3 months, you finally realize that, okay, maybe my partner is really good one, and I have to behave properly, something like that. And because you do not have kind of a fast reaction, maybe then if on some day the partner is not responding to your message, like within 10 minutes, after 3 hours and 4 hours, even like half a day, still nothing happened, because you are just a little bit slow and you did not really pick it up. You think, or maybe you think, yeah, you understand some bad mood can happen, and you wouldn't really overreact to this scenario. So this is a kind of example of a slow learning rate. So you slowly pick up your partner is a good partner, but when some negative outcome happens, you also do not overreact to it. So this is kind of a better understanding, I guess. So hopefully to help you understand the learning rate. So there's a question like, is this an individual difference cognitive pattern, or is it also a side effect of the task? Individual difference, I guess. Yeah. Some people, they do overreact to negative feedback and then they switch immediately. Some would say, well, this is because of randomness, because of probability, I ignore that, I do whatever I want. All right, make sense? Or questions? I think I need to stop. Yeah, I will. Questions? 3 seconds. 2, 1. Oh, good. Okay. So don't forget to log in your attendance. Well, there's a question. If you are used to unpredictable environment, you would probably benefit from high learning rate. Yes. Yeah, you might want to have a dynamic learning rate. Sometimes you want to be slower, sometimes you want to be faster. Depends on the environment. And this is the topic we will discuss next time. Good. All right, so don't forget to log in your attendance and also the review comments. That is next Sunday, I guess, whatever, you know the deadline. So have a good weekend and see you next time. Bye-bye.